A modern large language model can contain billions of parameters. But when it reasons, does all of that machinery participate equally? Or could something much smaller be happening inside? A specialized space where important intermediate ideas are gathered, transformed, and used. In July 2026, Anthropic published a remarkable study called Verbalizable Representations Form a Global Workspace in Language Models. And their question was simple. Can we actually find such a workspace inside a transformer? Their investigation gives us a new way to look at the transformer, not simply as attention plus MLPs, but also as the dynamics of information moving through a shared internal representation, a space every layer reads from and writes to. And this is why you should care. If you understand where information lives, how attention moves it, how MLPs transform it, and how a small set of representations can influence later computation, you begin to understand what a transformer is actually doing, not just what it produces. But how did Anthropic find this hidden structure in the first place? Before we talk about the Jacobian matrix, let me make one basic idea clear. How does information actually flow through a transformer? A transformer does not simply take a sentence and immediately produce an answer. Information is continuously transformed as it moves through many layers. At a particular layer, every token has an internal representation. You can think of this representation as a vector containing the model's current computational state for that token. For example, if the hidden dimension is 4096, then the representation of one token is a point in a 4096-dimensional activation space. Attention then allows that representation to gather relevant information from other tokens. The representation changes because it now contains information retrieved from the context. The MLP then transforms that representation. It can create new features and reshape the information before passing the result to the next layer. So, layer after layer, the representation keeps changing. Information is gathered, transformed, combined, and passed forward. And this gives us a useful mental model. The activation vector tells us where the model currently is in its internal representation space. Now we can ask the question that matters for our investigation. If we slightly change that representation, what happens to everything that comes after it? This is where the Jacobian matrix becomes important. First, let me tell you about the problem of activation. Then things will start getting unfold automatically. Suppose we pause a transformer in the middle of its computation and inspect one of its internal activations. At first glance, this seems like the obvious place to look for intelligence. But there is a problem. An activation vector may contain thousands of dimensions. Simply reading those numbers does not tell us which parts actually matter for the model's future behavior. Imagine two internal representations. One has a very large activation but barely affects anything downstream. The other is subtle, almost invisible, yet changing it completely alters the model's reasoning. Anthropic realized that looking directly at activations might be asking the wrong question. Instead of asking what an activation is, they asked what an activation does. To answer that question, they introduced the Jacobian Lens. Rather than simply reading an internal representation, the Jacobian Lens measures how changes in that representation influence future outputs. In Anthropic's words, the method focuses on the average linearized effect of an intermediate activation on future predictions. In other words, it measures influence, not appearance. And once they began looking at influence instead of activations themselves, a hidden structure started to emerge. What Anthropic found next was unexpected. Many of the most influential representations seemed to form a shared internal workspace. Suppose we pause a transformer in the middle of its computation and inspect one of its internal activations. At first glance, this seems like the obvious place to look for intelligence. But there is a problem. An activation vector may contain thousands of dimensions. Simply reading those numbers does not tell us which parts actually matter for the model's future behavior. Imagine two internal representations. One has a very large activation but barely affects anything downstream. The other is subtle, almost invisible, yet changing it completely alters the model's reasoning. Anthropic realized that looking directly at activations might be asking the wrong question. Instead of asking what an activation is, they asked what an activation does. To answer that question, they introduced the Jacobian lens. Rather than simply reading an internal representation, the Jacobian lens measures how changes in that representation influence future outputs. In Anthropic's words, the method focuses on the average linearized effect of an intermediate activation on future predictions. In other words, it measures influence, not appearance. And once they began looking at influence instead of activations themselves, a hidden structure started to emerge. What Anthropic found next was unexpected. Many of the most influential representations were not randomly scattered throughout the network. They appeared to organize into something resembling a shared computational workspace. We will now look at what a shared workspace is, how it appears across the layers of a transformer, and how the Jacobian matrix helps us identify it. Remember, a transformer has many layers. Every layer reads from and writes to the residual stream, which acts like a shared memory carrying the model's evolving representation forward. But the information represented in that stream is not the same throughout the network. Early layers are mainly building and transforming representations from the input. As we move deeper, increasingly abstract information emerges. Anthropic found something particularly interesting in the middle of this computation. There is a band of intermediate layers where a small set of representations begins to behave like a shared workspace. Think of it this way. Attention and MLP circuits throughout the network can write information into the residual stream. But some representations become especially useful because many different downstream circuits can read from them. That is what makes this workspace shared. It is not a separate box. It is a representational format that allows information produced by one part of the computation to become available to many other parts. And this is where the Jacobian lens becomes powerful. Instead of simply asking what a vector looks like, it measures how that representation influences future computation. When this analysis is repeated across representations and contexts, researchers can construct an influence map. Some directions have relatively limited downstream reach. Others compose broadly with the model's downstream weights. Those broadly usable representations are exactly what we would expect from a broadcast format. Information can be written once and then reused by many different computational circuits. And notice something important about the layers. The workspace does not simply appear at the beginning and remain unchanged until the output. It emerges at intermediate depths, evolves as reasoning proceeds, and eventually gives way to representations more directly tied to the final output. Now comes an even more interesting question. Can training change this workspace? Anthropic found evidence that post-training changes what appears in the model's workspace, including representations related to the assistant's behavior and responses. They also demonstrated counterfactual reflection training, where training the model to articulate principles in hypothetical reflection contexts caused related representations to appear in the workspace and improved behavior in the original context. And this points toward a much bigger possibility for AGI. Instead of only training what a model says, perhaps we can learn to deliberately shape the internal representations it uses while reasoning. Now let's discuss the mathematics behind Global Workspace. Don't worry, I will make it so simple that you will understand every piece of it. First, let's discuss what is residual stream and the maths behind it. Think of the residual stream as the evolving representation that travels through the transformer. At layer L, we can represent it mathematically as x superscript L. Now here is the important idea. A transformer layer does not simply throw away x and create a completely new representation. Instead, it keeps the existing representation and adds new information to it. This is where the word residual comes from. If a function f transforms x, the residual connection gives us something as simple as x plus f of x. In a transformer, that f is not just one operation. Attention contributes one update, and the MLP contributes another update. So, in a simplified mathematical picture, the next residual state becomes the current state plus an attention update plus an MLP update. We can write that as x superscript L plus 1 equals x superscript L plus a superscript L of x superscript L plus m superscript L of x superscript L. This equation is extremely important for our global workspace story because the residual stream is where information from different computational components comes together and continues into the next layer. So imagine attention discovering some information, the MLP transforming it, and both contributions being added into the same evolving representation. And now we have the mathematical foundation we need. The next question is, if we slightly change this representation, how much will the future computation change? Now we have an internal representation x, and we make a tiny change to it, delta x. The question is simple. After this tiny change, how much will the computation in the future change? Suppose the future computation is represented by y. Then y is some function of our current representation, x. If we change x by a small amount delta x, the future computation changes by some amount delta y. For a sufficiently small change, we can approximate this relationship using a linear transformation. And that linear transformation is the Jacobian matrix. Mathematically, we write j as the derivative of y with respect to x. And locally, the relationship becomes delta y approximately equal to j multiplied by delta x. This is the key intuition. The Jacobian tells us which directions in the current representation space can strongly influence the future computation. Move in one direction, and almost nothing may happen. Move in another direction, and the downstream computation may change significantly. Now imagine doing this not once, but across many representations and many contexts. We can begin to construct a map of which internal directions have strong downstream influence. And this is where the Jacobian becomes powerful for our workspace story. It gives us a mathematical way to look beyond what an activation looks like and ask how much that representation matters to everything that comes next. So let's bring everything together. We started with the transformer itself. Information flows through layers, carried by the residual stream, while attention gathers information and MLPs transform it. Then, we asked a deeper question. Instead of simply looking at an activation, what if we asked how much that representation influences the computation that comes after it? The Jacobian gives us a mathematical way to answer that question. A small change in an internal representation can be traced through future computation, revealing which directions have stronger downstream influence. And when Anthropic examined these influential representations across the model, they found evidence for a structured, shared workspace in intermediate layers. The important point is that the workspace is not another component added to the transformer. It is a way of describing a special pattern of information flow occurring within the existing transformer layers. This gives us a different way to think about intelligence in large language models. Not as something sitting in one neuron or one layer, but as information being gathered, transformed, shared, and reused across the network. There is still so much we don't understand, so until the next discovery, keep learning and stay curious.